All right, this is AP BC Calculus. We're doing a BC only unit. This is Unit 10, Section 12, Lagrange error bound. So essentially, we've already talked about alternating series error bound, and this is a different way to talk about bounding the error on a series. So it's also called Taylor's remainder theorem, and we'll go into this in a minute, but let's kind of look at the difference between, let's say you have some infinite series, right? So let's say you have some sum from n is 0 to infinity of some a sub n, right? That's the sum of the infinite series, right? Or actually, let's intentionally not use n's, just so I can say that the first n terms of a series. So let's use k, right? A sub k. All right. So we know that the nth partial sum, right, would be the sum from k is 0 to n of a sub k, meaning it would be a sub 0 plus a sub 1 plus a sub 2, blah 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 blah, all the way up to a sub k, right? A sub n, rather, right? So I stop at n. Okay, so that's the first n terms. So the argument would be that this, right, this infinite sum s is actually equal to the sum of the first n terms that we just saw here, plus some remainder that comes after. So this is the remainder of the series after the first n terms, right? After the nth partial sum, right? So r sub n, that's the notation of the remainder. So if this is the actual value of the series, right? Actual value, and this is the approximate value for the series using the first n terms, we could make the argument that the error between the actual and the approximate is basically just equal to whatever the remaining terms are, right? So this r sub n would be the n plus 1th term plus the n plus 2th term plus da-da-da-da-da, all the way up to whenever n is approaching infinity, right? Like the infinite terms. Like this would be infinite terms. So the idea is that the error of a series, right, is equal to this r sub n, right? This is the remainder of the series after the first n terms. So we're going to see an r sub n on the next page, and we're going to kind of talk about essentially the way that Lagrange error gives us a cap for that remainder. Okay, so I know that when you first look at this, it feels like a lot. It's color-coded because there's a lot going on, and I thought it might make it easier to figure out what's what, but let's kind of walk through this. So we already discussed this r sub n, right? In the last slide, we discussed about how that is basically the error in your approximation because you use the first n terms to approximate some infinite sum, so r sub n is your error, right? So we'll go ahead and write that that's the error, right? So our error is less than or equal to. So this is the n plus 1th derivative of f evaluated at some z, and this is going to be the weird part that's hard to get your head wrapped around. That z is going to be somewhere in the interval between x, which is the given x value, like if you're asked to use sine of 5, 5 would be the x that you're finding, right? And a is the value that your Taylor polynomial is centered around, which is quite often 0 because we're often dealing with Maclaurin polynomials, but not always. So x and a, x is going to be a number that's given, a is going to be the number that's given, z is some number in between them, and we'll talk about that in a sec because that's a little confusing. So x minus a to the n plus 1 is going to be pretty comfortable because we're going to know n. We're going to know that we used a 3rd degree Taylor polynomial, so we're using n plus 1, or whatevs, right? So 5th degree Taylor polynomial, so we're using n plus 1, fine. X is going to be given, a is going to be given. This is the mystery part that makes this problem harder. So the trick is that the way we deal with this is, since we don't always know what z value to plug in, we're going to look at the n plus 1th derivative as a function and ask ourselves what would be the maximum value of that derivative on the interval we have. We don't really care what the z value is. We just care that we pick the largest value of that n plus 1 derivative on the given interval. And we're going to walk through this. It's not as bad as it seems, I promise. But that's going to be the trick part, is that we want to max out this n plus 1th derivative on the interval that we're given. So let's walk through this. We're going to do a couple non-calculator ones. We'll do some calculator ones as well. So let's see how we do. All right, so first thing we're going to do is find the 5th degree Taylor polynomial, or Maclaurin polynomial rather, because we're centered at 0, for sine of x. It is absolutely fine for you to know what this is from memory. In fact, I'd recommend it, right? So it's better if you can do this without having to do any actual work. That's better. Great. You don't have to show work to find that Taylor polynomial. It's great if you memorize the series and you can just use it. For b, I'm going to use that to approximate sine of 1. So sine of 1 is approximately p sub 5 of 1, which is going to be 1 minus a 1/6, right, plus a 1 over 120, right? That's what 5 factorial should be. If I make everybody over 120, this is a 120 minus a 20 plus a 1 over a 120, right? So I'm pretty sure I get that sine of 1 is approximately 101 over 120. Oh, sorry, that should be approximate, my bad. All right. Last bit is I need to show that this error is less than 1 over 5,000. Well, the error, right? So the error, which is essentially the actual sine of 1, right? Sine of 1 minus my approximation for the sine of 1, right? That's my error. Should be less than or equal to. And then this is the part that's a little bit tricky. So the first part's pretty easy. I'm centered around 0 because it's a Maclaurin polynomial, right? So it's safe to say that I want x, which is 1, minus 0, which was my center, to the n plus 1. Now, one caveat about this is that I can't use, even though this is a 5th degree Taylor polynomial, it's sine of x. I can't use 6. N plus 1 is 6 because we need the next non-zero term, right? And the issue is that sine doesn't have any even powered terms. So I'm going to have to use to the 7th, right? Even though it's n plus 1, I'm going to have to recognize that that really this is actually the same approximation as the p sub 6 of x, because p sub 6 of x would actually be exactly the same thing because there is a 0x to the 6th term here. So I have to use 7. I have to use the next non-zero term over a 7 factorial. And then here's the hard part. I need to max out the 6th, sorry, my bad. I need to max out the 7th derivative of sine, right? So sorry, so we need to max out right here. This is my m, right? I need to max out the 7th derivative of sine of x on this interval, right? So so if f of x is sine, right? I also know that the 4th derivative is sine again because it's a loop, right? And then if I kept going, I could actually logically figure out that the 8th derivative, because every multiple of 4 is also a sine of x, right? So the thing I'm trying to max out is the 7th derivative, right? So the 7th derivative would be right before sine. It's a negative cosine, right? So if I want to max this out on the window from 0 to 1, well, here's 0. And since this is pi over 2, it's like 1.5-ish, right? So I'm trying to max out cosine on this interval. Its highest value is going to be the cosine of 0, which is 1. So that's going to max out at a 1. Now, you can kind of logically intuit that, to be perfectly honest. Sines and cosines basically max out at 1 on the intervals that you have. So that's so most of the time a sine and cosine maxes out at 1. So what that's going to do is that's going to say that this error, right? So this error, the error sine of 1, which is the actual minus p sub 5 of 1, it's going to be less than or equal to. And then I have that this is a 1 times a 1 over a 7 factorial. So essentially 1 over 7 factorial. And I was asked to show that that is less than 1 over 5,000, right? That's what I was asked. So if I figure out what 7 factorial is, I'll be honest, I don't have 7 factorial memorized. Some of you might, but I don't. I have 6 factorial memorized. I know that 6 factorial is a 720. So I would probably just do 720 times 7. And I'm going to get this. So sure enough, bigger denominator means a smaller fraction. So the error is in fact less than 1 over 5,000, right? Because, so this is my error, right? And it is less than 1 over 5,000, right? Bigger denominator means smaller fraction. There you go. You're going to see this a lot on the AP where they give you some number that maybe seems kind of random, like this 1 over 5,000, but when you clean up your denominator, let's say they give you 1 over 3,000, you might get that your answer is 1 over 3,200, right? So your 1 over 3,200 is definitely smaller than 1 over 3,000, right? So that's kind of the idea. All right, so you're going to go ahead and give another one a try, right? We're going to do the 4th degree or Maclaurin polynomial or Taylor polynomial centered at 0 for e to the x. Again, it's really better if you just have this memorized, right? It's not cheating. It's great, right? If you have memorized that this is what the Maclaurin polynomial for e to the x is, that's just dope. It's not cheating. Totally great, okay? Part B, and this is worth 1 point on the AP, and you're just expected to have it right. I just want to be really clear about that. There's not a lot of there's not really a lot of work expected. If you have to generate this Taylor polynomial or this Maclaurin polynomial from scratch and it takes you a ton of time, you're not getting any credit for the fact that that took you a ton of time. That's just a waste of your time, so please memorize it. All right, so I'm going to approximate it with this value, and I should have written an approximate. My bad. Take it back. Okay, so e to the first is going to be approximately, and then I'm going to make everybody over 24, right? So this is 24 plus 24 plus 12 plus 4 plus 1, all over a 24. It's a 48, right? And then a 60, so 65. 65 over 24. So that's my approximate value for e to the first, okay? Then I was asked to show that the error is less than e over 100, okay? Well, showing that the error is less than e over 100, so the e to the first, which is the actual minus my approximation, this is the error, right, should be less than or equal to. And then again, the tricky part is maxing out that quantity. It's easy to figure out what you're plugging in. You're just doing x minus 0 to the 1 more than 4th would be the 5th term. Again, the trick with sine and cosine was that they only use even or odd terms, so you can't do just 1 more than that. The bottom's going to be my n plus 1 factorial. So again, my n was 4, right? So n plus 1 will be 5. And then I need to max out, well, if the function is e to the x, then every single derivative, doesn't matter which one, is just also an e to the x, right? So if I want to max this out on the window from 0 to 1, the biggest value, and you can actually see this if you look at this graph, this is an e to the x graph. Here's 0, here's 1. The biggest value is going to be this one. So this is just going to max out at e, right? It's going to max out at e to the first. So if we skip down here, I'm going to get that the error, right, the difference between my actual e sub 1 and my my actual e to the first and my p sub 4 of 1 is less than or equal to an e divided by 5 factorial, right? Well, that's the same as an e over a $1.20. I was asked to show that that's less than e over a 100. Well, remember, bigger denominator, smaller fraction. So sure enough, my error, right, this would be the error because it's the difference between the actual and the approximation, is less than e over 100. Check. All right, so let's do example 2, also non-calculator. So we're going to write a 3rd degree Taylor polynomial, p sub 3 of x, for f of x about x equals 3, given this information. So we're given everything we need to write our Taylor polynomial, right? So p sub 3 of x should be f of 3, right, plus f prime of 3 times x minus 3 plus f double prime of 3 over 2 factorial times x minus 3 quantity squared plus f triple prime of 3 over 3 factorial times an x minus 3 quantity cubed. And then I was given numbers for all of those derivatives, right? So this is going to be f of 3, which is a 1, right, plus a 5 times the quantity x minus 3, right, plus this will be an 8 divided by 2 factorial, so that's a 4 times x minus 3 squared, right? And this will be a negative 12 divided by 6, so it's a negative 2 x minus 3 quantity cubed, right? So once I have that, so that's my p sub 3 of x, right? That was part A. First thing, write the Taylor polynomial. Okay. Second thing, use the Taylor polynomial. So f of 3.1 is going to be approximately whatever p sub 3 of 3.1 is. And we've seen this before, that it's pretty friendly when you end up with a 0.1, right? So this is going to be a 1 plus a 5 times a 0.1 plus a 4 times a 0.1 squared minus a 2 times a 0.1 cubed, right? So I get that this is a 1 plus a 0.5 plus a 0.04, right? Because this would be a 100th, right? minus a 0.002, because that would be a 1,000th. So I'm going to put all these guys together first, right? And I'm going to get that this is 1.54, and then I'm subtracting 0.002. And don't be ashamed, especially on non-calculator sections, to straight up write out the subtraction, because you're going to be surly if you get it wrong. So if you need to do it where you borrow, that's fine. If you're able to just do this in your head, that's also fine. Just don't be ashamed to be careful enough to get it right. I'm sure I've gotten it wrong at least one of these videos, but it's all right. All right, so there's my approximate value for f of 3.1. Last thing I'm asked to do is I'm asked to show that the maximum error is less than or equal to 1 over 2,000, given that I know a value for the fourth derivative of x, right? So, rather, the fourth derivative of f of x. So we know that the error, right, which is f of 3.1 minus p sub 3 of 3.1, so this is f of 3.1 minus p sub 3 of 3.1, right? We know that should be less than or equal to, well, it should be 3.1 minus 3 raised to the n plus 1, which would be fourth, right, over an n plus 1 factorial, right? And then this maxed out value, but they gave me the maxed out value of the fourth derivative, because they told me, hey, at the biggest it gets, it's a 10, right? They gave me that maxed out value. So that value, right, this f of 3.1 minus p sub 3 of 3.1 is less than or equal to. So this is going to be a 10, right, times, this is going to be a 1/10, right, or a 0.1 to the fourth, which we'll deal with in a sec. And on the bottom, I get a 24, right? So I'm pretty sure that that's essentially a 1 over 10 to the third divided by 24, or a 1 over 1,000 divided by a 24. If you do 1 over 1,000 divided by 24, it's the same as multiplying by 1 over 24, which means this is a 1 over 24,000, right? And I was asked to show that this is smaller than 1 over 2,000, which it definitely very much is, right? So I get that, and typically I probably was off by a decimal. I probably should have written this as, a 20,000 when I made it. I clearly was off by a decimal when I wrote it, but that's okay. So this thing is less than or equal to this, right? Bigger denominator, definitely smaller fraction. So that's true, right? So that this thing is definitely bigger than this thing. And there you go. All right, so when I wrote this, I definitely intended to make this a 20,000, not a 2,000, but I missed a 0 when I typed it, so there you go. All right, you're going to go ahead and give the same concept a try, right? Again, you're given a bunch of values for g of 5, g prime of 5, g double prime of 5, etc. You're going to write a second degree Taylor polynomial for g, right? So p sub, oh, sorry, I used q here, because I used q in this instance. It doesn't matter, but I use, oh, and see, it says q of 2. So q sub 2 of x is going to be g of 5 plus g prime of 5 times an x minus 5, right? Plus g double prime of 5 divided by 2 factorial times an x minus 5 quantity squared. And then I'm just going to use the values I was given, right? I was given g of 5 as a negative 2. I was given g prime of 5 as a negative 10, right? And I was given g double prime as an 18, so that'll be an 18 over 2, which would be a 9. All right, so there's my q sub 2 of x, right? So that was the first thing I was asked to do. The second thing I was asked to do was use my q sub 2 of x to approximate the value of g. So g of 4.8 is approximately q sub 2 of 4.8, right? Which is going to be a negative 2 minus a 10 times, well, this will be a negative 0.2, right? Plus a 9 times a negative 0.2 quantity squared, which we'll deal with in a sec. So that's a negative 2 plus a 2, right? Because that's what negative 10 times 0.2 would be. Negative 0.2 would be. And then plus this will be a 9 times 1/25th, because 0.2 is a fifth, right, and it's squared. So I'm pretty sure that's just a 9/25. That's my approximate value. So g of 4.8 is approximately a 9 over 25, right? Okay, so for part C, we're trying to show that the error, which would be g of 4.8 minus my approximation, oh, it was q, sorry, q sub 2 of 4.8, is less than or equal to. Now we want to show that it's less than or equal to 1 over 25, but we're going to go ahead and use the formula we know. So we know that we're going to use 4.8 minus 5 to the 1 power higher than the n, which is going to be a cubed, right, over an n plus 1 factorial, so that's a 3. And then the wild card is we have to max out the next derivative, but look, we were given that next derivative, right? And we were told, hey, it maxes out at, ooh, way too far, 25. So I just need to clean this up and show that whatever this number is, it comes out to be less than a 1 over 25. So this is a 25 times, so recall that this is a 0.2. It's a negative 0.2, but we don't really care. So 0.2 is 1/5, right? That's a negative 1/5 here. So I'm going to get a negative 1 over 125 rather, okay? All over a 6. That's what this thing is, right? Now the absolute value is going to take care of the negative, so I get that this is a 1/5 over a 6, which is a 1/5 times 1 over 6. I get that this thing is a 1 over 30. So basically, the error between my g of 4.8 minus my q sub 2 of 4.8, right? This is the actual, this is the approximation, is less than or equal to a 1 over 30, which is definitely less than a 1 over 25, right? Bigger denominator, smaller fraction. So I've shown that the error is less than what the cutoff was that I was given. All right, last two problems. Let's do something with the calculator. So let f of x equal e to the x over 2. If the second degree Maclaurin polynomial for f is used to approximate f on the interval from 0 to 2, what is the Lagrange error bound for the maximum error on the interval? So you're not actually asked to approximate, you're just asked for the Lagrange error, right? So the error, right, the error, which would be f of x minus, let's just say that it's p, they said the second degree Taylor, so p sub 2 of x, right? This would be the error, right? The error should be less than or equal to 2 minus 0, right, because it's a Maclaurin series, so we're centered at 0, right, over a, sorry, it's not squared, it's cubed, because it's n plus 1 over 3 factorial. And then the wild card is that you have to max out, right, you're going to have to max out f triple prime of x on the window from 0 to 2, right? So f of x is e to the 1/2 x, which means f prime of x is e to the 1/2 x times a 1/2, right? There's a coefficient of 1/2. F double prime of x, you're going to multiply by a half again. This is going to be a half times a half, which will be a fourth, right? When you do the chain rule, you'll end up with a 1/4. And then the triple prime of x, right, if you do the chain rule again, you're going to get a 1/8. So you're essentially maxing out this on the interval you're given. Well, since this is a calculator problem, right, I can go ahead and look at, sorry, we have lots of stuff in this calculator from before. I can go ahead and look at what 1/8 e to the 0.5x, right? I can graph it, and I know that the largest value is going to happen at 2, right? So I can just hit trace 2 and get that value, okay? So that y value that I have, right, that's going to be the max value. So there's two ways to do it. You can either put it in your calculator and trace it, right? But this is definitely going to be 1/8 e to the 0.5 times 2, right? That's definitely what's going to happen. That's going to be the max. And you can see that because if you picture what this graph looks like, and I also was able to graph it on a calculator, on the window from 0 to 2, this graph is going to be physically highest right there. Like if this is the interval I'm looking at, that's the highest. So basically my job is to type into my calculator this quantity, right? So I type in my calculator 1/8, it'll end up being an e to the first, right? Because it's e to the 0.5 times 2, right? Times an 8, because it's 2 cubed, right? Divided by that 3 factorial, which is a 6. And so I get C. So really, even though this is a calculator section, it's really only, or a calculator question, it's mostly only a calculator question because you would not be able to get the decimal by yourself. Let's try one more. So let f be a function such that we know that the fifth derivative of f is less than 0.8, right, on the window from 2 to 2.9. If the fourth degree Taylor polynomial about 2 is used to approximate the function on the interval, then the error bound tells you it must be within what amount. So again, really, you're using the calculator just to crunch the numbers, right? So f of whatever the x coordinate is that I'm given minus the fourth degree Taylor polynomial, so this would be the error, right? This is how we say error, right? Should be less than or equal to. And then we know it's going to be 2.9 because that's the biggest x on the window minus 2, right? Squared. Not squared, sorry, fifth. Come on, brain. Fifth. Over a 5 factorial, right? And then this should be the maxed out version of the fifth derivative, but we were given that it's a 0.8, right? So basically what I'm typing in my calculator is 0.8 times a 0.9 to the fifth all over a 5 factorial, and that's the decimal I want to find. So 0.8 times 0.9 to the fifth, all divided by, and if you know what 5 factorial is, you can certainly just type the 120. It's up to you. And so I get that it's this one, right? Because I get that this is approximately 0.0039366, but since we can either truncate or round, we're going to round in this case because that's the choice I was given. And that's the basic idea. It's just about memorizing the formula for Lagrange error bound and then being able to plug in the values.